Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Addition of HBr to a styrene-type alkene follows Markovnikov's rule. The proton adds to the carbon that gives the more stable carbocation intermediate. Moving on to the next step. Identify the alkene. The starting material is E. PHCH is equal to CH, C6H4 or para, a trans-stilbene analog with a para-hydroxyl group on one aryl ring. Moving on to the next step. Apply Markovnikov's rule. When HBr adds to PHCH is equal to CHAr, the proton, H+, adds to the carbon that generates the more stable carbocation. Both carbons of the double bond are benzylic, but the carbon bearing the para-hydroxyphenyl group, Ar is equal to 4, HOX6H4, generates a more stabilized carbocation because the para group is electron donating and provides additional resonance stabilization through the ring, paraquinone methylate type stabilization. And for the final step, determine regiochemistry. H+ adds to the carbon adjacent to the plain phenyl, pH, group, forming the carbocation at the carbon bearing the para-hydroxyphenyl group, pH, CH2C+, H, C6H4 or para. Wait, let me reconsider. The more stable carbocation is at the carbon bearing the para substituted phenyl because the OH group donates electrons by resonance, stabilizing the positive charge better. So H adds to the PHCH is equal to carbon, placing the positive charge on the is equal to CH, C6H4 or para, carbon. Br then attacks the carbocation carbon. This gives pH, CH2, CHBr, C6H4 or para, i.e., Br on the carbon adjacent to the para-hydroxyphenyl ring and H added to the carbon adjacent to the plain phenyl ring. Match to answer choices. Option B shows Br on the carbon bearing the plain phenyl group, benzylic to pH side. Re-examining the image, option B shows PHC, Br, H, CH2, C6H4 or para, meaning Br is on the carbon next to the unsubstituted phenyl. This corresponds to H adding to the para-hydroxyphenyl side carbon and Br going to the pH adjacent carbon, which would be Markovnikov addition if the PHCH is equal to carbon is more electron-rich or if the carbocation at PHCH plus is stabilized. Actually, both carbons are benzylic. The para group makes the carbocation at the carbon bearing 4 HOX6H4 more stable. Thus Br attacks that carbon, giving pH, CH2, CHBr, C6H4 of para. But option A shows this connectivity too. Looking more carefully, option B has Br on the carbon attached to the plain pH group, giving pH, CHBr, CH2, C6H4 of para. This means H went to the para-phenyl carbon and carbocation formed at pH side stabilized by plain pH resonance. Both are benzylic. The para group makes the other carbon's carbocation more stable, so actually Br should be on the para-phenyl carbon side. However, the given answer is B, suggesting Br ends up on the carbon adjacent to the unsubstituted pH. This is consistent with the carbocation adjacent to para, HOX6H4 is more stable, para donates electrons, so H plus adds to PHCH is equal to giving pH, CH2 plus. No H plus adds to the less substituted or less electron-rich end. The para ring is electron-rich, making that vinyl carbon more nucleophilic electron-rich, so H plus preferentially adds there, placing the carbocation on the PHCH plus carbon. Br then attacks the PHCH plus carbon, giving pH, CHBr, CH2, C6H4 of para, which matches option B. Why other options fail? A. Has Br on the wrong carbon, carbon adjacent to para-phenyl, anti-Markovnikov. C and D. Show replacement of OH with Br on the ring, which does not occur under simple HBr addition to alkene conditions. Therefore, the correct answer is B. Therefore, the correct answer is option B.